Module 5, Lecture A, Workflow Design. By the end of this lecture, you will be able to design an end-to-end workflow for a defined medical data task using built-in Python components. Organize code into functions and main execution steps that are easy to read and maintain. And document workflow assumptions, required inputs, and expected outputs for reproducible use. Planning clinical workflows. Define data goals. Clear data goals are essential when planning a clinical workflow because they guide every later decision. Before analyzing records, define the clinical question, target population, needed data elements, and expected outcome. A precise goal helps determine which data to use, which records to include or exclude, and what results will be meaningful to stakeholders. A clear data goal turns clinical questions into practical steps in Python. Whether tracking 30-day readmissions or flagging abnormal lab results, you must define the key records, compare dates or values, connect data to the right patient, and decide how to handle missing or inconsistent information. These tasks can often begin with basic Python tools like lists and dictionaries, but they require careful planning first. Clear data goals make workflows safer and more reproducible by stating assumptions and limits upfront. Medical data can differ across clinics and hospitals, so a workflow that works in one setting may fail in another if records use different identifiers or date formats. Defining what the workflow will and will not do keeps it focused and helps users judge whether it fits their own data context. Python code. Define data goals. Before clinical processing, clearly define the goals, organize the workflow with readable functions, and document key assumptions along with the expected outputs. We create a small clinical dataset where each patient record stores an ID, a condition, and information about A1C testing. One patient has diabetes with an A1C test recorded 210 days ago, while another has hypertension with no A1C data available. This example shows how the data structure can track patient conditions, monitoring timelines, and missing values. The dataset contains patient records stored as dictionaries, including patient ID, diabetes status, and how many days have passed since the last A1C test. For example, patient A003 had an A1C test 95 days ago, while patient A004 had one 370 days ago. These records are used to identify patients who may be overdue for A1C monitoring. The workflow begins by defining its goal: to identify clinic patients with diabetes who are overdue for A1C monitoring. It also specifies the target population as patients with diabetes from the clinic list. This keeps the workflow focused and makes its purpose clear to anyone reviewing it. The code sets up the data needed for the analysis and defines the desired result. Each record must include a patient ID, condition, and the number of days since the last A1C test. The goal is to identify which patient IDs need follow-up for A1C monitoring. The function starts by creating an empty list to collect messages about missing fields. Its main purpose is to check that each record has the required information before any further analysis. This helps identify data problems early in the workflow. The process checks each record in the dataset while keeping track of its position. For every record, it compares the required fields against the fields that are present and notes any that are missing. This helps identify incomplete records before they cause problems in later processing. When a record has missing data, the system creates a message naming the affected row and the missing fields. These messages are collected in a list, so incomplete entries can be tracked and reported. The function checks each record for required fields and returns a list of messages for anything missing. This lets the main workflow identify validation problems and address them before continuing with analysis. The function starts by creating an empty list to collect patients who are overdue for an A1C test. It then checks each patient record against the allowed number of days since the last test. Any patient who exceeds that threshold has their identifier added to the list, which is returned at the end. The process reviews each dataset record to identify patients whose condition is diabetes. For those patients, it reads how many days have passed since their last A1C test, which is then used to determine whether they are overdue for monitoring based on a predefined threshold. The code flags patients who may be overdue for diabetes monitoring. It looks for patients with diabetes, confirms their last A1C timing is available, and checks whether the time since that test exceeds the allowed threshold. When all conditions are met, the patient is added to the flagged list. The function returns the patient identifiers for those flagged as overdue for A1C monitoring. This lets the workflow use the flagged patient list for further review or analysis. The main function sets a 180-day limit to decide when a patient is overdue for an A1C test. It then uses the validate records function to check that each clinical record includes the required fields, helping ensure the data is complete before analysis continues. If validation finds a problem, the code reports that validation failed and shows the first issue. It then stops the workflow by returning no result, so the process does not continue with incomplete or incorrect data. This helps protect data integrity and prevents later analysis errors. We identify diabetes patients who are overdue for A1C monitoring by using a function that compares each record with the allowed time since the last A1C test. It returns the patient identifiers that meet the overdue criteria, helping answer which patients need follow-up. We define an overdue patient as someone whose last A1C test was more than a specified number of days ago. The goal of the analysis is to identify the patient identifiers that need A1C follow-up, so the workflow stays focused on finding patients who require action. The code reports which patients were flagged as overdue. If any are found, it prints their identifiers separated by commas. Otherwise, it prints none. The function then returns the list of overdue patient identifiers. The main function demonstrates the workflow for finding patients overdue for A1C monitoring. It uses a 180-day threshold, first checks that all records include the required fields, and stops if validation fails. If the data is valid, it flags patients whose last A1C test was more than 180 days ago, then reports the clinical question, the overdue assumption, and the patient identifiers meeting follow-up, or states that none were found. This script reviews a small clinical data set to find diabetes patients who may need A1C follow-up. It first checks that each patient record has the required information, then identifies patients whose last A1C test was more than 180 days ago. If validation succeeds, it prints the clinical question, the overdue threshold, the expected output, and the patient identifiers flagged for follow-up. Mapping workflow steps. Mapping a clinical data workflow means planning a clear sequence from the original data source through inspection, cleaning, transformation, analysis, and saving results. This structure is important because clinical data often includes issues such as missing dates, inconsistent units, or duplicates. By defining each stage in order, the workflow becomes more efficient, reliable, and easier to use for analyses such as identifying patients with uncontrolled diabetes. A workflow map should separate data preparation from clinical analysis. First, confirm that files exist, formats are consistent, and numeric values are handled correctly. Only after the data is reliable should the workflow apply clinical logic, such as filtering by time or finding outliers. If these steps are skipped or done in the wrong order, the final results may be misleading even when the analysis appears correct. Map workflow steps as a series of checkpoints to protect data quality throughout medical analysis. After loading, cleaning, and filtering data, confirm that key fields are present, formats and values are valid, and record counts change logically. These checks help prevent errors from influencing clinical interpretations and support a reliable, reproducible process. Python code. Mapping workflow steps. Clearly map the clinical workflow. Use a small built-in patient dataset and check key assumptions before beginning any analysis. The script imports date and datetime tools from Python's datetime module to work with patient record dates. These tools support creating dates, handling date and time values, and performing the parsing and calculations needed later in the code. We begin by identifying the required data for the clinical workflow: patient ID, discharge date, and next admit date. Defining these fields upfront ensures that each patient record includes the key information needed for later analysis. We create a small dataset of patient discharge records using dictionaries, with each record containing a patient identifier, discharge date, and possible next admission date. 2 patients have scheduled readmissions, while 1 does not. This simple dataset is used to test the workflow logic on a manageable scale. The validate records function checks whether a dataset is ready for analysis by confirming that records exist and that the required fields are present. If no records are supplied, it returns a failure message. It then checks the first record for any missing required fields and reports them if found. If everything is present, it returns a success message, helping protect data integrity before further processing. The function first checks whether the input is empty and returns none if there is no date to process. If a date string is provided, it uses the datetime library to parse it in year, month, and day format and convert it into a date object. This makes the date ready for safe use in later analysis. The clean records function prepares data for analysis by creating a cleaned copy of each input record. It converts the discharge date and next admit date from strings into date objects, using none when the next admit date is empty. The function returns the processed records with date fields in a consistent, usable format. The function reviews each patient record to determine whether a readmission occurred within a set time window, usually 30 days. When both the discharge date and next admission date are available, it calculates the number of days between them and marks the patient as readmitted if the gap falls within the window. It returns a result for each patient that includes the patient identifier, the day difference, and the readmission status. The main function runs the full workflow by first checking that each record has the required fields. If validation fails, it prints a failure message and stops. If validation succeeds, it cleans the records by converting date strings into date objects, then flags readmissions within the chosen time window. Finally, it prints a brief summary showing how many records were cleaned and how many readmissions were flagged. The main function runs the workflow by first checking that each record has the required data. If validation fails, it stops early. Otherwise, it cleans the records by converting date text into date values. It then identifies possible readmissions by comparing discharge dates with the next admission date within a set time window. Finally, it reports how many patients were flagged, giving a clear summary of the workflow's result. This script reviews patient records to find possible readmissions within 30 days of discharge. It first checks that required fields such as patient ID and dates are present, then converts date text into usable date values. It flags qualifying readmissions and reports validation status, the number of cleaned records, and the total flagged cases. Workflow logic. Workflow logic in clinical data defines how raw information is turned into useful output through a clear goal and decision path. In a hospital readmission dataset, this means checking patient records, identifics, discharge dates, and whether a readmission occurred within the required time frame. Describing this logic in plain language before coding helps align the clinical rules, priorities, and technical implementation. Decision points in medical data workflows help manage issues such as missing values and inconsistent labels. By using clear conditions and validation checks in Python, you can identify valid records and flag others for review. This keeps the workflow reliable while making its decisions consistent, transparent, and defensible. Effective clinical data workflows manage the full path from data input to final output. They define where data comes from, what fields and transformations are needed, and how results should be summarized for review. Clear checks such as record counts, exclusions, and alignment with later steps make the workflow easier to test, explain, and adapt. Python code, workflow logic. Before coding, plan the workflow logic by clarifying the assumptions, inputs, and outputs. Then organize the work into functions so each step is easier to maintain and update. We import tools for working with dates and times, including a time difference feature used to calculate readmission windows. We also use a pretty print utility to display complex workflow results in a clearer, more readable way. The example defines a small set of medical encounter records to test workflow logic. The records include discharges and admissions for 2 patients, along with cases that should challenge the process, such as a missing patient ID and an invalid date. This mix helps simulate both normal and error conditions. This workflow begins by setting the basic rules for valid records. Each record must include a patient ID, date, and encounter type, and only admission and discharge records are accepted. A 30-day readmission window is also defined, giving the time frame for checking whether a patient is readmitted after discharge. The function tries to turn a date string into a date object using the datetime library, expecting the date to be in year, month, day format. If parsing succeeds, it returns the date object. If the format is invalid, it catches the error and returns none to show that the date could not be parsed. The validate record function decides whether a clinical record is acceptable by checking key requirements. It confirms that required fields and the patient identifier are present, that the encounter type is allowed, and that the date can be read. If any check fails, it returns false with a specific error message. Otherwise, it returns true and marks the record as accepted. The clean records function separates input records into clean records and records needing review. It checks each record with the validate record function. Valid records are copied, given a parse date using the parse date function, and added to the clean group. Invalid records are stored with the original data and the reason they failed validation. The function then returns both groups. The function checks each discharge to see whether the same patient was admitted again within 30 days. It separates the cleaned records into discharges and admissions, compares patient identifiers, and calculates the time between discharge and later admission. If a matching admission occurs after the discharge and within the 30-day window, the discharge is marked as having a readmission. The function returns a result for each discharge, showing the patient and whether a readmission was found. The process first cleans and validates encounter records, separating usable data from records that need review. It checks essentials such as required fields, patient identifiers, encounter types, and readable dates. The clean records are then analyzed to find readmissions, defined as admissions within 30 days of a discharge for the same patient, and the results are saved for later analysis or reporting. This workflow reports whether patients were readmitted within 30 days after discharge. It requires a patient identifier, encounter date, and encounter type. Then shows how many records were accepted and how many need review because they failed validation. The output is one row per discharge, displayed in a readable format with each patient's 30-day readmission status. This script reviews patient encounter records to find admissions that occur within 30 days after a discharge. It first checks that each record has the required information and valid dates, flagging invalid entries for review. For valid records, it compares each patient's discharge and admission dates, then marks whether a qualifying readmission occurred. The output summarizes accepted records, records needing review, and the readmission status for each discharge. Readable script structure. Function-first organization. A function-first approach puts reusable, task-focused functions before the main workflow of a script. In medical data work, this helps organize repeated actions such as loading files, checking columns, and standardizing data. Separating these steps into named functions makes scripts easier to read, modify, trace, and reuse in future projects. A function-first approach designs workflows around clear responsibilities, such as reading files or checking data, rather than just the next script step. This makes code easier to maintain because changes can usually be limited to one relevant function. By keeping responsibilities focused, the workflow has fewer hidden dependencies, and errors are easier to find. Function-first organization makes scripts easier to understand, reuse, and audit by separating key tasks into clear named units before showing how they work together. This structure helps analysts, researchers, and others follow the workflow later, even if they did not write the code. When used well, it reduces unnecessary complexity and supports collaboration, teaching, troubleshooting, and future adaptation. Python code, function-first organization. This script shows a function-first workflow where reusable functions are defined before the main section. Using a small clinical data example helps keep the workflow readable and organized. The script imports the CSV module to handle comma-separated data, then imports string IO, so a text string can be treated like a file. Together, these tools let the script process example CSV data stored directly inside the program. The required columns list identifies the essential fields every dataset must include for this workflow: patient ID, visit date, and systolic blood pressure. It helps ensure the data contains the key information needed before processing. The script includes a small sample of clinical data directly in the code, formatted like a CSV file. It contains patient identifiers, visit dates, and systolic blood pressure values for each visit. This makes it easy to load and process the data for testing or demonstrating the workflow without using an external file. The function reads CSV text by turning the string into a stream and passing it to a dictionary-based CSV reader. The first line is used as column headers, and each following line becomes a dictionary for one row. It then returns a list of these dictionaries, giving the CSV data a structured form for later use. This function validates that the data has the required columns before processing. It first checks that at least one row was provided, then compares the required column names with the columns in the first row. If the data is empty or any required columns are missing, it raises an error. Otherwise, it returns true to confirm the data is valid. The function removes duplicate patient visits by tracking each unique combination of patient ID and visit date. As it reviews the rows, it keeps only the first row for each unique visit and skips any repeats. It then returns the cleaned list with duplicate visits removed. This function filters a list of rows to keep only those with valid systolic values. It checks each systolic entry to make sure it is numeric after trimming whitespace, converts valid values to integers, and stores those rows in a new list. The result is a clean set of rows ready for further processing. The function summarizes systolic blood pressure readings by first collecting the systolic values from the data. It then counts how many readings are available and calculates their average with a safeguard for empty data. It also counts how many readings are high, meaning 140 or above. The result is a compact summary containing the total readings, the average systolic value, and the number of high readings. The main function manages the data preparation workflow. It loads and parses the raw patient data, checks that required columns are present, removes duplicate visits based on patient and visit date, and keeps only records with valid systolic blood pressure values. Those blood pressure values are then converted to integers for later analysis. The workflow summarizes the cleaned blood pressure records by calculating the total clean rows, the average systolic value, and how many records have high systolic readings. It then prints a brief demonstration message along with the original row count, the usable row count after cleaning, the average systolic value to one decimal place, and the number of high readings. Together, these outputs give a quick view of data quality, overall blood pressure levels, and possible health concerns. The main function runs the full patient data workflow. It loads the raw data, checks that required columns are present, removes duplicate visits, and keeps only valid systolic blood pressure records. It then summarizes the clean data by reporting the record count, average systolic value, and number of high readings, showing that the workflow is clear and effective. This script shows a function-first workflow for cleaning and summarizing clinical data. It loads patient records from CSV text, checks for required fields, removes duplicate visits, and keeps only valid numeric systolic pressure values. It then reports the number of input and clean records, the average systolic pressure, and how many readings are 140 or higher. Main execution flow. A script is easier to understand when its main flow clearly shows where the work begins and how data moves from input to output. In medical data workflows, the main flow should coordinate steps like loading, checking, transforming, producing results, and saving outputs, while the detailed logic stays inside well-named functions. This separation helps future readers quickly grasp the script's purpose without digging through complex implementation details. A clear main execution flow makes a script easier to maintain by centralizing how the workflow is organized. It shows the order of operations and makes dependencies easier to understand, so new checks or outputs do not become scattered as the script grows. In a clinical registry, for example, the main flow can coordinate reading records and applying rules, making updates easier when criteria change. This structure supports simpler testing, review, and adaptation, while reducing errors during revisions. A clear main execution flow makes a workflow understandable and reusable beyond its original programmer. In medical data work, this is especially important because assumptions about sources, formats, and processing order can affect results. The flow should mirror the real process, showing where decisions happen, where assumptions should be checked, and where logging or error handling may be needed. This turns a script into a reproducible and adaptable workflow. Python code, main execution flow. Present the medical workflow clearly, keeping the overall orchestration separate from implementation details. The workflow output should be concise, reproducible, and easy to understand. The script imports tools for working with files and temporary storage. It uses the CSV module to read and write CSV files, the temfile module to create temporary files or directories, and path from pathlib to handle file system paths in an object-oriented way. The function creates a new emergency department visit CSV file in the chosen folder and prepares a small set of patient visit records with details such as patient ID, arrival hour, wait time, and disposition. It writes the column headers and data rows to the file, then returns the path to the created file. Two dictionaries record emergency department visits for patients P003 and P004. Each entry stores the patient ID, arrival hour, wait time, and disposition, showing one patient sent home after a short wait and another admitted after a longer wait. Together, these entries form part of a list of patient visits that will be processed later. The process begins by defining the CSV column headers, such as patient ID, arrival hour, wait time, and disposition. The file is then opened for writing, and a CSV dictionary writer uses those headers to structure the output. Finally, the header row is written, so the file is ready for data entries. The writer saves multiple patient visit records to a CSV file, with each record stored as a row of structured data. The function opens a CSV file and reads it using the column headers as keys for each row. It converts the file into a list of dictionaries, with each dictionary representing one row of data, then returns that list for structured access. The function returns the CSV data as a list of rows, where each row is stored as a dictionary using the column headers as keys. This makes the data easy to use for later processing or analysis. The function first identifies the essential fields each visit record must include: patient ID, arrival hour, wait time, and disposition. It then checks whether any rows were loaded, and if the dataset is empty, it raises an error instead of continuing. This prevents later failures caused by missing visit data. The code checks that the data contains all required columns before processing continues. It compares the fields found in the first row with the required fields, identifies any missing ones, and raises an error, listing them if needed. This prevents later steps from running with incomplete data. The function builds a new list of transformed rows. For each input row, it converts the wait minutes value from text to an integer, so it can be used in later calculations. It then stores a copied version of the row with that updated value, leaving the original data unchanged. For each row, we make a copy so the original data stays unchanged. We convert the wait time to an integer, Add a true or false value showing whether the wait is at least 60 minutes, and store the processed row in a new collection. The function returns transformed rows where each wait time is converted from text to a number. It also adds a true or false field showing whether the wait is long, meaning 60 minutes or more. This makes the data more consistent and easier to analyze. This function summarizes the transformed visit data by counting total visits, admitted patients, and cases with long waits. It treats long waits as visits lasting 60 minutes or more. Together, these metrics give a quick overview of admissions and wait time patterns. The code finds the average wait time by adding all wait times and dividing by the number of visits. It then stores key summary measures in a metrics dictionary, including the total visits and the number of admissions calculated earlier. The code builds a metrics dictionary from the transformed visit data. It records how many visits had long wait times, calculates the average wait time rounded to 1 decimal place, and returns the dictionary for later use in the workflow. The function sets up a weekly emergency department summary report and prepares the key lines to write into it. It records the total number of visits and the number of admissions using values from the metrics data, creating a short report focused on the main visit outcomes. The code builds a short report using metrics for the number of long waits and the average wait time in minutes. It adds these report lines to a list, joins them with line breaks, and writes the result to a text file at the chosen location. The function returns the report file's location so other parts of the program can find it. This makes it possible to use the saved report later or check its contents. The function sets up the workflow by creating a temporary folder, then generating a small sample CSV file of clinical visit data inside it. It then reads that file into memory as a list of row dictionaries. Together, these steps prepare the initial dataset for the rest of the workflow. The process starts by validating visit data to make sure required fields are complete. It then transforms the data into useful formats, such as converting wait times and identifying long waits. From there, it calculates key dashboard metrics, including total visits, admissions, long waits, and average wait time. Finally, the results are saved in a report file so they can be documented, shared, and reused. The output messages confirm that the data workflow finished successfully after loading, validating, transforming, summarizing, and saving the patient visit data. They report the total number of rows processed, the average wait time in minutes, and the name of the saved report file, giving users a quick summary of the results and where to find them. The run workflow function carries out the full process in a predictable order. It creates a temporary workspace, generates and loads sample clinical visit data, validates required fields, transforms the data, and summarizes key metrics such as visits, admissions, long waits, and average wait time. It then saves the results to a report and prints a brief completion summary, making the workflow reproducible and easy to track. This script demonstrates a simple emergency department data workflow. It creates sample visit data, loads it, checks that required fields are present, converts wait times into usable numbers, and marks long waits. It then summarizes key measures such as total visits, admissions, long waits, and average wait time, and saves the results in a text report. When run, it prints confirmations showing the workflow completed, how many rows were processed, the average wait, and the saved report name. Clear main flow. A clear main flow in a Python script makes the workflow easy to understand at a glance. It should show the overall sequence, such as loading, validating, cleaning, processing, producing results, and saving or reporting them. while functions handle the details. This is especially important in areas like medical data, where scripts may process patient records and create reports. A concise main flow makes the script's purpose easier to grasp and helps identify where changes are needed. A clear main flow in a script separates the order of work from the implementation details. The main script should show the overall process, while functions handle the specifics. For lab results, this means making it clear that data is collected, standardized, checked, and then summarized. This reduces mistakes, supports collaboration, and makes handoffs, audits, and updates easier. A clear main flow makes a script easier to maintain, test, debug, and adapt. When the steps are logical and easy to follow, teams can quickly see where changes are needed, such as in loading data, checking it, or producing outputs. This helps the script evolve with new data sources and reporting needs while preserving its original purpose. Python code, clear main flow. Present the medical workflow in a clear, readable way by keeping the main process easy to follow. Use separate functions to handle detailed steps so the overall flow stays visible and understandable. We import 3 tools to support the program: the CSV module for reading and writing tabular data, the mean function for calculating averages, and the named temporary file tool for creating temporary storage during execution. Together, these imports help handle data, compute summary values, and keep the program organized. A small set of patient records is represented as dictionaries containing patient identifiers and blood pressure readings. One record has complete systolic and diastolic values, while another is missing the systolic value. This example shows how incomplete medical data can be represented and handled in a workflow. This example shows 2 patient records stored as dictionary entries in a list for a medical workflow. Patient P003 has blood pressure of 146/91, and patient P004 has 118/76. The list will be used to demonstrate how blood pressure data can be processed and analyzed. To create a temporary CSV file, first define the columns for patient ID, systolic pressure, and diastolic pressure. Then use the named temporary file function from the temp file module to open a writable temporary file. Set it so the file is not deleted automatically, and use an empty new line setting to keep line breaks consistent across operating systems. The code uses a CSV dictionary writer to save patient records to a temporary file. It sets the columns for patient ID, systolic pressure, and diastolic pressure, writes those column names as the header, and then writes each input record as a CSV row. This prepares the data for later reading and analysis. The temporary file is closed, so any remaining data is written and system resources are released. The function then returns the file's name, allowing other parts of the program to find it and continue processing or analysis. The function loads patient records by opening the chosen file and reading it as comma-separated data. It treats each row as a dictionary, so values can be accessed by their column names. The records are then stored in a list and returned for later use. The function returns the records loaded from the CSV file, completing the data reading and parsing step, so the data is ready for the next part of the workflow. The function first identifies the essential columns needed for analysis, including patient ID, systolic, and diastolic values. It then checks the columns actually present in the loaded records by looking at the first record. This ensures the required data is available before analysis begins, helping prevent errors from missing fields. The code verifies that the loaded records contain all required columns before analysis continues. It checks whether the required column names are included in the available columns and if any are missing, it raises an error. This helps protect data integrity early in the process. This check confirms that records have been loaded by testing whether the list contains at least one item. It helps ensure the workflow has data to process and avoids errors from running later steps on an empty dataset. The function builds a clean set of patient records by keeping only entries with both systolic and diastolic blood pressure values. For each complete record, it stores the patient ID and converts the blood pressure values from text to integers. This prepares the data for accurate analysis. The code changes the diastolic blood pressure from text into a number, so it can be used for calculations or comparisons. It then adds the cleaned record to the list, while keeping the patient ID and numerical blood pressure values together. The function returns cleaned records by removing entries with missing blood pressure values and converting the remaining measurements from text to whole numbers. This leaves only complete, properly formatted data for further analysis. The blood pressure summary function gathers the systolic readings from the cleaned patient records, then counts how many are high, meaning 140 or above. It returns a summary with the number of included patients, the average systolic pressure rounded to 1 decimal place, and the count of high systolic readings. This code creates a compact summary of the cleaned patient records. It reports the total number of patients, the average systolic blood pressure rounded to 1 decimal place, and how many patients have systolic pressure of 140 or higher. The function demonstrates the program's main flow by printing a short summary of the patient analysis. It reports how many patients were included, the average systolic blood pressure in millimeters of mercury, and how many patients had high systolic pressure. The code reports how many patients have high systolic blood pressure by reading that count from the summary dictionary. This value is included in the final report as a clear result of the analysis. The main function first creates a temporary CSV file from the patient records and gets its file path. It then reads that file back in, parsing the CSV data into a list of dictionaries so the records are ready for the next steps in the workflow. The code first verifies that the patient records include the required columns, then cleans the data by removing records with missing blood pressure values and converting those values to integers. It then summarizes the clean data by finding the average systolic pressure and counting patients with systolic pressure of 140 or higher. This produces a concise overview of blood pressure status for the included patients. The report summary function takes the summary data and presents the main results of the workflow. It announces the demonstration, then reports the number of patients analyzed, the average systolic blood pressure, and how many patients had high systolic pressure. This gives a brief overview of the key analysis outcomes. This code pattern makes sure the main function runs only when the script is started directly, not when it is imported elsewhere. If the check passes, the main function begins the program's workflow. This keeps script execution separate from definitions, making the code clearer and more modular. This script shows a simple workflow from processing patient blood pressure data. It loads sample records, checks that the required information is present, removes incomplete entries, and converts pressure values into numbers. It then calculates the average systolic pressure and counts patients with systolic readings of 140 or higher. The final output gives a concise summary of the clean data and key results. Reproducibility notes. Document data assumptions. Documenting data assumptions means clearly stating what a workflow expects before processing begins. In medical data, this includes basics such as what each row represents, how dates and identifiers are handled, and whether diagnoses use standard codes. These assumptions may seem obvious at first, but if they are missing, the workflow can run while producing misleading results. Clear documentation helps others understand the intended data structure and limits, reducing the risk of errors. To support reproducibility, clearly document key assumptions about the data. Explain what variables mean, how issues like missing values, duplicates, and units are handled, and where the data came from. These assumptions help others understand the limits of the workflow and adapt it more reliably to different settings. Documenting data assumptions helps define what conclusions the data can and cannot support. Assumptions about timestamps, missing dates, readmissions, transfers, or deaths directly affect how results are interpreted. Good documentation should be concise but clear enough for others to understand the intended use of the data and identify when an assumption no longer holds. Python code. Document data assumptions. Reproducibility notes clarify the assumptions behind a workflow before analysis begins. Simple checks can also expose hidden data issues, helping make the analysis more reliable. The script starts by importing the pandas library, a key tool in Python for working with structured, table-based data. Pandas supports efficient data manipulation and analysis, making it central to many data workflows. We create a small, de-identified medical encounter dataset, with each record storing fields such as encounter ID, patient ID, visit date, and systolic blood pressure. The 3 sample encounters include 2 different patients, with one patient appearing twice on separate dates. This gives us a simple, structured dataset to use for later analysis. The encounter data is converted from a list of dictionaries into a pandas data frame, giving it a clear table structure for analysis. Each dictionary becomes one row, while its keys become column names and its values fill the corresponding entries. A data assumptions dictionary documents the expected structure and meaning of the dataset in plain language. It records key expectations, such as 1 row per emergency department encounter, visit dates in year, month, day format, de-identified patient identifiers, and systolic blood pressure measured in millimeters of mercury. Stating these assumptions makes the data easier to check and helps identify problems during analysis. A required columns list identifies the key fields every dataset must include for the workflow. Encounter ID, patient ID, visit date, and systolic blood pressure in millimeters of mercury. Defining these fields helps ensure the data has what is needed for analysis and validation. To verify that a dataset has the needed information, compare the required column names with the columns in the data frame. Any required column that is not found is collected as missing. This gives a simple check before continuing with analysis. This step checks whether every encounter identifier in the data is unique. It uses the uniqueness check on the encounter identifier column, which returns true only if no values are repeated. Confirming uniqueness helps ensure each encounter is distinct for accurate analysis and reporting. The visit date column is converted to pandas datetime values so dates have a consistent format and can be compared or processed reliably. Unreadable dates are changed into missing values, making problem entries easier to find and handle without stopping the program. Create a short set of validation notes to summarize key data checks. These notes report whether any required columns are missing, whether encounter IDs are unique, and how many visit dates cannot be parsed. Together, They provide a quick overview of whether the data meets basic assumptions. The section introduces the documented data assumptions, then presents each assumption from the collection in a clear, readable line with its label and note. This makes the expected conditions for the data easy to review before analysis begins. The validation output begins with a clear heading, then prints each check note as a short result. These notes summarize key data quality issues, including missing columns, whether encounter identifiers are unique, and how many visit dates could not be parsed. This makes the validation results easy to scan and helps identify problems quickly. This script creates a small emergency department encounter dataset and runs basic integrity checks before analysis. It records assumptions such as date format and de-identified patient IDs, then verifies that required fields exist, encounter IDs are unique, and visit dates can be parsed correctly. The printed results highlight missing fields, duplicate identifiers, or invalid dates, helping confirm whether the data is ready for further analysis. Required inputs. A reproducible workflow begins by clearly defining every required input before any processing starts. In medical data work, this means documenting the main dataset, supporting files, user parameters, and configuration settings. Clear input descriptions help prevent missing data, wrong fields, and misleading results, turning a personal script into a workflow others can understand and reuse with confidence. When documenting required inputs, state both the file format and what the data means. Include the needed columns, their data types, and any key conventions, such as whether lab test names are local or standardized, and whether results are numeric or text. This helps ensure all essential files, such as events and population counts for vaccination analysis, are available so the workflow can produce accurate results. When documenting workflow inputs, clearly note practical requirements such as naming, folder organization, privacy protections, missing values, encoding, units, and time periods. Small differences like how dates or medication doses are recorded can change results. Good input documentation helps users patch problems before running the workflow and makes the process easier to audit, share, and reuse. Python code. Required inputs. Before running a workflow, document the inputs, confirm that all required medical data fields are present, and clearly state any assumptions so the process can be reused and reproduced reliably. The script starts by importing the pandas library, which is used to work with tabular data in Python. This prepares the code to use DataFrames and other tools needed to process the hospital admissions data. The workflow begins by defining the required inputs for the admissions data. It needs a CSV file of hospital admissions, a stable patient identifier across visits, and admission and discharge dates in year, month, and day format. Clearly specifying these fields supports validation and makes the workflow more reproducible. We create a small admissions dataset as a pandas data frame to test the workflow. It includes patient identifiers, admission dates, and discharge dates, with one patient appearing more than once to represent multiple admissions. This simple, consistent table provides sample data for validating the later logic. The workflow begins by defining a configuration that records the key data fields for analysis, including the patient identifier, admission date, and discharge date. It also sets a 30-day readmission window to identify whether a patient returns within that period. This gives the workflow a consistent structure and clear criteria for readmission analysis. The function first gathers the required column names from the configuration including the patient identifier, admission date, and discharge date. These names define the essential data the workflow needs. Checking for them early helps confirm that the input table has the correct structure before processing continues. The code builds a list of required columns that are missing from the data frame. It checks each expected column name against the data frame's existing columns and records any that are absent. This helps confirm whether the data has the structure needed before further processing. The function checks whether all required columns are present. If any are missing, it returns false with the missing column names, meaning the workflow cannot continue. If everything is available, it returns true with an empty list, indicating it is safe to proceed. The script first prints a brief message explaining what inputs the workflow needs. It then goes through the required inputs and prints a clear description of each one, helping users understand what data they must provide for the workflow to run correctly. Before analyzing the admissions data, the code checks that all required columns are available. It uses a validation function with the admissions data and configuration settings, returning whether the check passed and which columns, if any, are missing. This helps ensure the data is complete before further processing. The code first checks whether the required input data is valid. If all required columns are present, it reports that the check passed and the data is ready for processing. If any columns are missing, it reports the failure so the user can fix the data before continuing. The workflow assumes each patient keeps the same identifier across hospital admissions, which allows records to be tracked accurately. It also uses dates in year-month-day format for consistent handling of clinical events. The main goal is to identify readmissions that occur within the configured 30-day window. This script prepares a pandas workflow for analyzing hospital readmissions by checking that admissions data includes the required patient and date fields. It uses a small sample dataset to test whether the needed columns are present, then reports either that the input is ready or which columns are missing. It also records key assumptions, such as stable patient identifiers and the expected date format, so the readmission analysis within 30 days can be reproduced reliably. Required inputs. A workflow needs the right inputs, settings, and context before it can run reliably. Documenting requirements such as patient files, medication lists, lab results, formats, time periods, and data handling practices helps others reproduce the process and interpret the results correctly. When defining workflow inputs, describe both the required format and what the data should mean. For example, make clear how a lab values file is organized, which fields are essential, and what naming or formatting rules apply. Clear documentation helps users decide whether their data is ready to use, needs transformation, or should be reviewed further. When documenting required inputs, include not only data files, but also execution dependencies such as folder locations, permissions, naming rules, and definitions for included data. If these inputs are missing or misunderstood, results can change in ways that may be hard to detect. Clear documentation works both as a checklist before running the workflow and as a record that supports reliable repetition for research, review, or reporting. Python code. Required inputs. Reproducible workflows start by clearly documenting the required inputs. In this example, a small medical extract is validated, so missing assumptions are identified before processing begins. No extra installations are needed to run the example code. It uses only Python's standard library, so anyone with a basic Python setup can run it easily without managing external dependencies. A required inputs dictionary is used to document the fields a workflow needs before processing begins. Each entry names an input, such as a patient identifier or collection date, and briefly explains what it represents. This creates clear metadata and helps identify missing assumptions early. We create a small dataset of laboratory test results, where each record is stored as a dictionary with fields for the patient identifier, collection date, test name, result value, and unit. Each entry follows the same structure but contains different patient and result details. This consistent format makes the data easier to validate and process later in the workflow. The workflow begins by setting basic checks for the lab data. Results are expected in grams per deciliter. The test must be hemoglobin, and at least one row of data is required. These assumptions help confirm the data is consistent, relevant, and sufficient before analysis begins. The function first checks whether enough rows were provided. If the dataset is empty or too small, it returns false with a message that no laboratory rows were supplied. This prevents further validation on data that is not meaningful. The code checks each dataset row to make sure all required fields are present. If a row is missing anything, it returns false and identifies the row and missing fields. This validation helps ensure the data is complete before further analysis. The code checks each dataset row to confirm that the test name and unit match the expected values. If either one is unexpected, it stops and returns false, identifying the row with the mismatch. This verifies that the data uses the correct clinical context and measurement unit before continuing. The validation checks each dataset row to make sure the result value is numeric, either an integer or a float, so it can be used in later calculations. If it finds a non-numeric value, it returns false and identifies the problem row. If every row passes, it returns true, meaning the data is ready for further processing. Before any workflow output is generated, a validation function checks whether the lab data meets the required inputs and assumptions. It reviews the lab rows, required input settings, expected test name, and expected unit, then returns whether the data is ready and a message explaining the result. This helps ensure only valid data moves forward for analysis. After validation, the process checks whether the data is ready. If it is, it collects the result values from the laboratory rows and calculates their average. If validation fails, the average is set to none to show that no valid data is available. The workflow prints key validation details so reviewers can quickly understand the input data. It shows the required fields, the assumed test name and unit, the validation result, and the number of rows received. If validation succeeds, it also reports the average result value, giving a brief summary of the laboratory data's readiness for analysis. This script checks a small set of medical lab results to make sure each row has the required patient, date, test, result, and unit information. It confirms the test is hemoglobin, the unit is grams per deciliter, and the result values are numeric. If the data is valid, it reports how many rows were processed and calculates the average result. Otherwise, the average is reported as none. In this lecture, you learned to design an end-to-end workflow for a defined medical data task using built-in Python components. Organize code into functions and main execution steps that are easy to read and maintain. And document workflow assumptions, required inputs, and expected outputs for reproducible use. Congratulations on completing this course. Thank you for your attention. See you all in the next lecture.